Good evening, everyone. Welcome to the last lecture of the week of the online course of the International Master in Quaternary in Prehistory. I introduce you tonight Pierre Voinchet, who accepted to teach you some of his specialties. So Pierre Voinchet is a professor in the Muséum National d'Histoire Naturelle of Paris. He's a geochronologist. That's why tonight he will present you the dating method in prehistory and quaternary geology. Pierre, the floor is yours.
Thank you very much. Hello, everybody. So now, as Julie said, we are talking about dating method. Sorry for those already knows all those I will talk about, but I think for main part of you, some part of what I will talk is totally new or not totally really known. So I try during 1 hour to explain you how we can give age for archaeological site, prehistorical site, geological site, paleontological, etc., etc. Which method we can use and why we choose to apply this method or one other. It depends of many different things. And I try to explain why it is more efficient to use this one or another one in regards of the type of site we search to know the age. So the first thing, why we try to date prehistory. If you work on a site, you found you will find a lot of artifacts, remains, many things. But if you want to compare with another site, if you want to know the duration of the existence of a specific species or behavior or technique or something like that, you need to have a good chronology. You have to have the possibility to fix in time the beginning and the end of different process, and also try to give specific age of one phenomenon appears in an area or in a site, in a stratigraphy or something like that. So for that, we have to try to find into the site some elements change during the time after the deposit, after the occupation of the site. And this element, if they change in regards of natural behavior, it is possible to use them as a chronometer, a geochronometer. So hopefully we have many different object material we found into a site that could work and to be usable as a geochronometer. The most evident, it is not in relation with human activities, is minerals we can find forming the background of the site, but sometimes we have also elements directly in relation with human activities. So in many type of site, open air site or into a cave, we have different supports that we can use. We can use carbonates, stalagmite, floor, or speleothem if we are in cave, but also carbonates in association with living material like shell or something like that. We can use teeth and bones of big mammals in every kind of site. Sediment also can be used to give age. And in this sediment, some specific ones, the volcanic minerals, are very usable. We will see that after. For the most recent site, we can also find and use wood and charcoal. We talk about that. Everybody knows the C14 radiocarbon method. It's well known, but not really useful for the whole extension of prehistory, but it's very useful. And in some time, in association with this charcoal, we can find also some minerals heated intentionally or not, rocks submitted to the fire, and all these elements could be used in order to provide age of something happens into the site. Ça marche plus. Si, ça marche. So, on this different support, we can apply many different methods. Each support contain different elements, evolute with a specific process, and in order to use them as a chronometer, we have to multiply to use a different kind of method based first on the direct observation, direct logical analysis of what we found. It is the stratigraphical and geological method. We will see few of them to explain what I want to say using this term. Sometimes in the support, some chemical elements change with time, but not in relation with radioactivity, just chemical process. It exists few methods based on this phenomenon. We will talk quickly about that. But you see here the two last, not square, but in the yellow and in the red, it is the most useful method in order to give precise age, not precise. Absolute age, it's not the good term, but absolute age. It is based, they are based, sorry for my English, on radioactivity and the effect of radioactivity on the different materials. So I will explain main of this method very quickly, how we can use them, on which kind of support we can use them, and what is the limitation of each of these methods. So you see here the time range of each of these methods. Each method have a limitation in terms of time range, because the process we try to analyze and to understand is very particular for each method, and we have some limitation in time for all of them, and we will see after why we have this kind of limitation. For example, in time, you can see, I don't know if it was here, the C14, the radiocarbon, the small thing you have there. Even it is the most well-known method, it's very useful, very precise, but you see it's very limited in time. We can just apply it for the last 50,000 years. You see, we have many other methods with different time range for their application. And you see here the first thing we have to think about when we try to give an age to a site or to an element we found into the site. It is the first idea we have about this probable age of the site, because you see here it is not possible to use all the method for all the quaternary period. We have to select which method we suppose we can use to give an age to a very old site or a very young site. You see here, we have to select what we can apply, if it is a C14, if it is a uranium, thorium, argon, optically stimulated luminescence, etc., etc. The first thing to have in mind, to keep in mind, it is the time range application of each of the method we will try to apply. The second thing, it is also to know well which support, which material we found into the site, because these materials cannot be usable with all the methods. Each method, it's applicable on one specific material and not on all the material. So we have, you see here, this table in order to know if one method is possibly usable on our site because we found the specific materials good or not so bad to give an age. For example, for the C14, you see here, it is possible to apply on wood and charcoal, coral, bones, and a small part on speleothem, and that's all. If you find only burnt flint, volcanic rocks, or quartzite sediment, you cannot use this method. And you see it's the same for all the different methods. So now, if you work on a site and you want to give an age to specific level of your site, you understand you have two things to take into account. First, the probable age of your site in order to know which kind of method you can apply. And in the second time, if you have or not the good support to apply this method. If one of these two different elements it is not sure, you cannot date your site. It's sad, but so when we try to date, so we have to take into account all this phenomenon, all this thing. But also we have to keep in mind which kind of event we will date using one method or another method, because each beginning of the time lapse, when we put on the chronometer, it is not the same for all the material. It is not the same for all the method. And we have here in this table few examples of support, event, and method we can apply. For example, for the carbonate, the first line, we date the crystallization, the formation of the carbonate, and we can use, for example, U series. It is totally different if we work on teeth and bone, because for this material, we don't date the crystallization, the formation of the bone, but the death of the animal. You have here the method we can apply for this specific support. And you see, for each this kind of support, of material, we date different phenomena. So sometimes it's difficult when you try to compare age obtained on different sites, on different level of different sites, to compare what it is exactly the age you can use, because sometimes you don't have age obtained by the same method, and you don't give the age of the same event. Sometimes you try to compare dating obtained on sediment, so it is in relation with the transportation and the deposit of sediment. And if you compare with teeth you find in another level, sometimes you can obtain age totally different, but in fact it is logical, because here it is you date the global environment of the site, and when you date the death of the animal, so the teeth and the bone, you date an archaeological fact. So keep in mind, sometimes it is difficult to compare specifically two different age. Age is just a number with a plus or minus something, but you have to take in account to keep in mind which event you really date using this material or this material, this method or this method. So we will talk about that after. So very quickly, because I know Alison and Christian talk about these different aspects just before, but the first thing when we work in geochronology, it is to observe very carefully the site, because the first method we can apply, it is about relative chronology. And the first thing we have to do, it is to understand the relation, the logical relation between each level, each support we try to date. And for that, we have to apply the stratigraphical method and to understand the relation between the different level we try to date, in fact. So very quickly, I hope Christian talked about that yesterday or just before, or Alison also, because it is the basement of the stratigraphical approach and the understanding of what it is a stratigraphy. So the principle of stratigraphy are really simple, but very, very, very useful in order to understand and to compare the different results you can obtain in the same site or between different sites. The first principle, it's continuity, saying the same level have the same age on each part of this level, very, very simple. The second one, superposition, say when you stack different elements, creating a stratigraphy, the oldest is at the bottom and the youngest is at the top. It is very useful because when you have no specific material usable on the site, because perhaps it is too old or you have a bad conservation of the specific material usable with different geochronological method, just the observation and the understanding of the stratigraphy can give you an idea of the chronology. For example, here we are in Turkana, and just this observation and the understanding of the relation between the different levels allows first to classify and to give a chronology for the some of the first representatives of our species in very large view, because different skulls have been found in different beds of these different geological steps, and it is easy to understand that bed 1 is older than bed 2 and bed 2 is older than bed 3. And if you find the different skull in bed 3, 2 and 1, you know who is the oldest, who is the youngest. It's very simple, but very powerful in order to understand and to try to describe an evolutive process, for example, for human evolution or something like that. The two last stratigraphical principles, it is the first one, it is cross-checking, saying if you have an event creating alteration on an existing, pre-existing element, it signifies that this disturbing event is youngest than what it is disturbed. It's difficult for me, sorry. For example, here, you see we have 1, 2, 3, 4 level, logical. 1, it is the oldest, 4, it is the youngest. We have a fault here in 5, so it significates the movement, the fault movement, 5 is youngest than 4, 3, 2, and 1. The cave in 6, digged into the 4th level, it significates this cave is youngest than the 4th level. It's totally logic, but it's very powerful also because sometimes you have some elements imbricated, and it's easy to know who is the first, the second, the third, in order to give a chronology of different events could disturbing existing stratigraphical level. And the last one, the paleontological identity said when you found the same fossil assemblage in 2 different levels, that significate these 2 different layers have the same age. For example, if you find the same microfaunal remains in 2 different levels of 2 different sites, if you have a good idea of the age and the specificity of this microfaunal remains, you can say these two levels are coeval, are strictly at the same age. Passons. And these two different things, the cross-checking on the paleontological identity is very useful sometimes when you have disturbation of the logical stratigraphy. Here it is the same site I showed you just before in Olduvai Gorge. You recognize here the first picture, but if you go here in the small valley, you see we have very strong disturbation due to tectonic activities of the logical stratigraphy, bed 1, 2, bed 1, 1, 1, 2, 3, etc. And you see here we have very complicated stratigraphy, but it's easy to build the story of this deformation because we can find the same elements, the same minerals, the same lithic assemblage, the same faunal assemblage in different levels, and it's easy to make correlation just in the two parts of this big element, disturbed or not disturbed by tectonic. So it is just observation, understanding, but very powerful in order to build the chronology of an area on different sites we can find in this area. No. Sorry. And I will begin with different methods we can use to date now a site based on something evolved during the life of a specific living element and change with time and can give an idea of chronology of the age without chemical process or radioactive process. The first method we can talk about now, it is the dendrochronology. Dendrochronology, it is based on the analysis of the circle, the growth circle we can find into a trees. You know, a tree year by year grows and build a new growth circle from the center to the external part of the tree. But what it is very interesting is that the thickness of the circles depend of the climate and the climatic event, the climatic change occurs during the life of the tree. If we have one very bad year for the tree, for example, dry event or a very cold event, the thickness of the ring, the tree ring is very small. But at the opposite, if it is a very good year for the tree, a lot of water, good temperature, etc., etc., the thickness of the ring tree is very, very large. So during all the life of this tree, the tree record the climatic change on a specific area. And it is easy to build this kind of code showing the total climatic history occurs during the life of the tree. And now, if we have many different trees with different age on the same area, it is possible to build for each this kind of code and try to correlate code by code, tree by tree, and try to build the climatic history for a very, very long period. So when you build this kind of scale, if you find a piece of wood in this area of the same kind of tree, it is possible to correlate its specific code to the global scale and to know exactly when the tree have been living, if it is very old or not. And it's very, very powerful method because with that, it is possible to give an age with uncertainty of 6 months. It's very, very, very powerful, but you have to find the good tree, and it is not always evident. So, some example of what it is possible to date. The second method, not based on chemical process, it is paleomagnetism and archaeomagnetism. You know, during Earth's history, the polarity, the magnetic polarity of Earth changed. We have some inversion. This inversion of magnetic field, Earth's magnetic field, it is recorded by different geological elements, lava flow, but also sediment, and it is possible to determine the record polarity and to know if the level you are working on is in a normal polarity, like today, on inverse polarity. So it allows to put your sample in this kind of big chronology. It is not a real dating method, but sometimes if you have another idea of where you are in time, it is possible to discriminate if you are just below or after a big magnetic inversion. So it's also very useful. For example, it is used to specify and to clarify some dating of, for example, here human remains in part where we have a lot of different lava flow recording very well all the inversion and all the moving of magnetic field. So it works. For the very recent period, we can also use not the inversion of the global magnetic field, but just few variations, small variation of the magnetic field. It's the base of what we called archaeomagnetism. And you see, for example, here, the direction of the geomagnetic North Pole in 1947 and in 2006, it's not the same. And it moved year after year. And this movement of the North geomagnetic pole, it is recorded in different elements, for example, brick, lava flow, etc., etc. And it is possible to follow the movement of the North geomagnetic pole between at least the 3-4 last 1,000 years. So if you found now a brick not alterated, and you can show the orientation of the paleo geomagnetic field, it is possible to put the direction on this diagram and to know precisely the age of the last cooking of this brick. So, sorry, it is very, very. I speak very quickly because we have not so much time and there's a lot of methods. Now we will talk about the method based on a physico-chemical phenomenon, but not in relation with radioactivity. The first one, not so much used, but it works. It is the racemization of amino acids. It is based on a specific process that occurs in the amino acid after the death of something living. During the living part of the living of individual, all the amino acid have one specific form. It is the Lavoisier form of these amino acids. For example, here for alanine. And after the death of an animal, the Lavoisier alanine transforms to dextrogir alanine. Lavoisier dextrogir, it's a capacity of these amino acids to to moved to interfere with the light. Levogir, it's significant if you put a ray light into this material, it's go to the left. Dextrogir, it seems the ray go to the right. And you see here, after the death of an animal, all it is Levogir at the beginning, and time after time, Levogir will be replaced by Dextrogir. And if you dose how many Dextrogir and Levogir you have for one specific amino acid, it's possible to say since how many times the animals is dead. Another one, it is obsidian hydratation, not based on the same process. Here, what it is very interesting, it is in relation with the water penetration into a stone, specifically obsidian, after the flaking of this specific raw material. Because this material, it is in fact glass, and this glass is very poor in water, and when it is exposed to water we can find in atmosphere, this water go into the flake. And the thickness of the part altered by the water can give you the time lapse between the flaking and now. So it's very, very useful, very powerful, because it is the only one method that can give you an age of a real archaeological fact, a real movement made by prehistoric human. But it's very difficult to use, because first you have to find obsidian first, and to know very well the atmospheric condition, the ratio of water we can find in atmosphere during a long period in the specific area, to be sure of the speed, the time necessary to go into the flake. So now we will talk about what we use more. We use more in order to give age to prehistoric site, and what we call absolute age. Absolute age is just we can give an age with a number. Before it's difficult, but with this method it is possible to say our age have dated from medium Pleistocene, 325 kiloyears before, etc., etc. The first family of methods, it is a radiometric method. Radiometric method, it's significant. These methods are based of the appearance or disappearance of specific chemical element, but radioactive element. It is a method where we have to know and to determine the ratio between a father element and a daughter element, because due to the radioactivity, some element disappears and are transformed in other element by the time. For that, we use we use the law of radioactivity. Radioactivity said it is in fact the ability of specific element to disintegrate, to transform into another element. So you have here, the red line and the blue line. The red line correspond to the father element, which disappears with disintegration, and the blue line, it is the daughter element, appears because it is the transformation of father element. These two different curves are strictly the same for all the radioactive elements. What it is changed between one element to the another element, it is the half-life or the period we have between the transformation of 50% of the original father element. The kinetic process is the same for all elements, but the time elapsed between 100% of father element to 50% of another element depends of the element, and it is the radioactive half-life. For example, for the C14, to pass to from 100% to 50%, take 57 and 30 years, 57,030 years. For the 40 potatio, it's more than 1 billion years, and for the 238 uranium, it's more than 4 billion years. It is the same curve, but for C14 here, we have just 5,070 and 7,300 years. For 14 potassium, it's more than 1 million, etc., etc. Okay, and you see here the limitation of all this method. It's when all the father element disappears, it is not possible to use this specific element to date the support that you try to know the age. To determine the amount of each of father and daughter element, we can use different approach. The oldest one, it is by direct radioactive counting using gamma spectrometer, and it's a measuration of the number of disintegration we have by second, for example. So it gives you an idea of the amount of the element you try to determine, but it takes a lot of time to do that, and you need also a very important samples, a lot of material in order to do this measurement. So it's why now we don't use this method. We use mass isotope counting using spectrometer, mass spectrometer and accelerator, because for that we count directly the ratio of the different elements we try to found into the support. For that, it's very, you can do that quickly, and it's more precise than using a gamma spectrometer. For example, for C14, now we can work with few grams, for few milligrams of material. With gamma counting, we need more than 10, sometimes more grams to do the same analysis. So you see, it's better to use mass spectrometry. Okay. So using in this family of radiometric method, we use essentially three different elements in prehistory and quaternary geochronology, depending of the material, as you know, and the time range where we are. The first one, it is the C14, but it's usable on the very young sample. With that, we try to date the end of the prehistoric period and the beginning of historic period. We will see how it works after. The second one, it is the 40 potatio. You see here the time range is very, very important, but the problem, it is just possible to apply on volcanic material. And the third one we will talk about, it is the thorium and uranium couple working in a time range between now to 700, 800 kiloyears. We will see why just after. For the C14, very quickly, you see here, it is just possible to date something have been living in the past. It is just possible to date wood or bones or teeth, but something in relation with the living activities. Why? Because the C14, it is produced in the high part of atmospheres by interaction with nitrogen element and the solar and cosmic activities, creating C14. This C14 disappears after, but not so quickly. So this C14 make association with oxygen, creating carbon dioxide, but radioactive carbon dioxide. This carbon dioxide is used by trees, grass, algae, and other vegetables in order to produce matter. And all this matter is radioactive. And it is in equilibrium with the ratio of C14 we can find into the atmospheres. The animals eat the grass or the trees or the leaves, exactly the same, in order to produce meat. So meat and bone and all the things. It significates all the animals eating grass and vegetables are in equilibrium with the C14 we found into the trees, but also in the C14 we found into the atmospheres. And the animals eating the animals that eating the vegetables, etc., 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 are also in equilibrium. But this equilibrium is disrupted at the death of the animal or of the trees, because there's no exchange with the atmospheres after this death. And after that, progressively, slowly, the ratio of C14 decrease into the support we can use now for dating. And here we are at the death of the animal, for example, at 100% of C14 in comparison with what we found into the atmospheres, and progressively and regularly the ratio diminishes, the contents, the C14 contents decrease into the bones, in the tree, etc., etc. And the quantity, the amount of C14 we can find allows to say to find the age of the death of the animal. But you see here, after 7 or 8 half-life period, there's not enough C14 into our support to continue to use it for dating, because when we arrive here, you see there's less than 10% of C14, so it's very difficult to give a precise and accurate age after this limit. But you see, it's very useful for the last part of prehistory, the first part of history, but it is not possible to use for very, very old period. Another problem with C14, it is the production of C14 into the atmosphere. It is not constant in time. It's evolved in relation with the solar wind, and also in relation with the evolution of the magnetic field. So, in fact, we know now the amount of C14 in atmospheres change in time, and we have to take into account this change in order to calibrate precisely the age we obtain with this method. For that, we date with two different methods, C14 and another method, the same element. For example, here a tree. We have the age obtained by C14 and the age obtained by dendrochronology. We know this one is very good, and this one, you see, it's not so accurate. There's a problem in relation with the evolution of the ratio of C14 in atmospheres. So it is possible to determine the gap between the two different results. So we know for this age, we have this gap, this systematic in all the sample we have for this age. When we have this gap, it is possible to apply now another sample where it is not possible to do the two different kind of dating. For example, here we work on deer skull, and we just have the C14 age because it's not possible to do the dendrochronology. But as we determine here the gap, in order to correct the age we obtain for this time range, it is possible to determine here the real calibrated C14 age. It's why into literature you will heard about calibrated C14 age. Calibrated significates it is corrected. We correct the deviation of the ratio, the difference of production of C14 in atmospheres during the time. So for that, we create this curve, allows to know precisely how to correct our C14 age if we are in a very young samples or in very old. For all the period, it is possible now to correlate and give some calibrated age. So I pass. Another method based on practically the same event, it is the cosmonucleide method, because C14 is one of these cosmonucleide, but it exists other elements created by the interaction of cosmic rays and Earth environment. C14, it is the nitrogen, but you see here there's other element could be transformed by the interaction with cosmic ray. And these elements are accumulated in different support, like here minerals, and it is possible to determine the ratio of these different elements and give the age of the beginning of the interaction between cosmic rays and these specific minerals. So that can give you a way in order to date the deposit of sediment, for example, or the digging of a valley or something like that. It's very powerful in order to date sediment and the exposition to the solar ray and also the cosmic ray of this kind of minerals. It's this method used for to make dating because there's no other support near the Paleo Lake, Chad Lake, only sediment, and this sediment have been exposed to the cosmic ray since the deposition times to the covering of this deposition time. So it is possible to determine this very complex story of denudation, sedimentation, transportation, etc., and give an age of all the sedimentary deposit in which they found many fauna and also human remains. The second method, not in relation with cosmic ray, it is the argon method or potassium argon method based on the transformation of 40 potassium to 40 argon. This is very useful in order to give an age for all volcanic elements because of these two different elements, the father and the daughter. The father, it is a solid, so you find it into the rocks naturally, and the daughter, it is a gas. So when you melt rocks, what it occurs into a volcano, all the pre-existing argon is released, because as it is a gas, if the rocks become liquid, the argon are totally released during this first phase. And when the rocks crystallize, when we pass from magma to rocks, the phenomenon stop, and the argon could not go out after this crystallization. And the ratio of argon, the quantity of argon, increase and increase and increase and increase due to the disintegration of 40 potassium. So if you have an idea, if it is possible to give the ratio between argon and potassium, it is very easy to date the crystallization of the rocks, so the volcanic event. So it's very useful if you work in a volcanic area, like here it is the east part of Africa. But it is not the only one. If you work in Italy, for example, there's a lot of volcanoes, and it is very useful to use this method in order to know precisely the age of the different level you can find in the stratigraphy with ash inside, and you can give the age of the site of human occupation just in between of two different levels. So it's very, very useful, but you need to have a volcano in the vicinity. The last radiometric method, it is the uranium series method. For this one, the two different elements that we take in account, it is thorium and uranium. What it is very interesting here, that's the two different elements are not gas, are solid, but one of them, the uranium, it is possible to dissolve into water, but thorium, it is impossible. So uranium moved with water into the ground, but thorium not. So in this kind of environment, the water dissolve carbonate and produce some speleothem when it arrives into a cave or into a spring or something like that. And this carbonate, at the beginning, only contain only uranium and absolutely no thorium, because thorium still into the mother rocks, and only the uranium moved with the water. But after a few times, uranium contained into the speleothem begin to disintegrate, and it is transformed in thorium. So now if you determine the ratio between thorium and uranium, it is possible to give precisely the age of the formation of the speleothem. It is very interesting because it works also for the teeth and the bone of big mammals, not due to the crystallization, but when you have fossilization of a bone, the organic part disappears and it's replaced by mineral parts. And these mineral parts contain just uranium at the beginning, and after the total fossilization of the bone, uranium begin to transform to thorium, and it is also possible to determine the precise age of the fossilization of a bone using this method. For example, yesterday, Christian talked about la cône de l'Arago. It is one of the methods, one of the most powerful method used in this cave in order to give the age of the different stalagmitic floor, divided the site in different big parts, but also in order to give age of on teeth and bones of big mammals in this kind of site. The last thing I will take just 10 minutes to finish the last part of the last family of method we used in geochronology. It is the paleodosimetric methods. These methods are also based on radioactive activity, but not on a specific element transforming in other, but it is based on the effect of the radioactivity on the rocks or minerals or bones or something like that. Why? Because when an element is transformed in other, there's ray or particle are emitted, and these particle or ray are very energetic and transform and create some defect in crystal, in bones, and something like that. And it is possible to determine how many defects are produced in 1 year, how many defects have been produced during all the history of the element we try to date, and if it is possible to determine precisely these two different quantity, it is possible to say since how many times the phenomenon occurs. So it gives the age of a specific phenomenon. It depends of the material we analyze and the specific method we try to use. The first one, it is not used now. It is now totally not used because it's very complicated and it's work on very few materials. It is a fission track, so I don't talk about that. We work more on a method, thermoluminescence, optically stimulated luminescence, and also electron spin resonance based on the same physical process. It is the ionization of a part of a minerals by the alpha, beta, and gamma ray produced during the disintegration of radioactive element. These different rays ionizing the minerals, that it significates it gives energy to an electron. These electrons are ejected from the atom where it is before, and it is released into the crystal. And sometimes it exists some traps, some paramagnetic traps that catch the element, the electrons, and year after year, the quantity of trapped electrons increase into the crystal. And it is what we have here. It is here at the beginning of the story of the crystal. There's no electrons trapped into the paramagnetic trap. And you see year after year, the amount of trapped electrons increase and increase and increase and increase and increase. But you see, it is not a linear distribution. You see, there's a saturation process because these paramagnetic traps are not so much into the crystal, and when they are totally filled, it is not possible to trap a new electron. So it is one of the limitations of this kind of method. So when it is saturated, even if you let the sample 1 million, 2 million years in the same place, it is impossible for it to record the time. Okay. The first one, it is the thermoluminescence. Thermoluminescence, for the three methods I will talk now, the only difference is the way how to determine how many electrons are trapped into our crystal. For the first one, it is due to the temperature. If you give some energy, thermal energy to the crystal, the trapped electrons are free, and this freeing of the electrons create light. And the intensity of the light is directly in in regards with the quantity of electrons initially trapped into the crystal. So when we try to date this kind of element, we increase slowly the temperature and we determine when we have the different peak of light emission, and we try to understand and to quantify how many electrons are free at this moment. Okay, so for that, this method is very useful if you try to give age to elements have been heated into the past. Because when you burn a piece of rocks, you released the old trapped electrons and you reset the signal. And in fact, after this resetting, if there's some radio element in the vicinity, the amount of electron, the trapped electron increase, and it is this moment you try to date. This method has been used in many places, essentially for period where the fire is very clearly used by men, and it allows is here you see, for example, in the Levantine corridor, to determine the real stratigraphy, the real relation between the different sites, and it allows to show that it is not as the first archaeologists think, we have Neanderthal before Sapiens and Neanderthal after. It's very complicated, and it is a good thing shown by this kind of dating. So the second method, quite based on the same process, it is the optically stimulated luminescence. Here, in fact, it is like for thermoluminescence, we try to free the trapped electrons, giving some thermal stimulation, but this thermal stimulation, in fact, it's given by a laser pulse. And here, what it is interesting, it is we don't date the last cooking of something, but the last light exposure. Why? Because, in fact, the trap were used for this method are very sensitive to the solar light. Solar light allows to the release of all the trapped electrons. You have here the curve. You see during the geological history of our minerals, we have the amount of trapped electrons increase and increase and increase and increase. And during the phase of erosion, transport, and deposition of the quartz grain or the feldspar grain we have here, all the trapped electrons are quickly released. And after the deposition, after the formation of a level into a strata, into a site, when the grain are not still not exposed to the solar light, the quantity, the amount of trapped electron increase, and it is possible to determine the archaeological dose. So it is the dose received by our sample in relation to the amount of electron we can find into this crystal. So it allows to give the age of the deposition of specific strata of sediment. The problem with this method, it is the sensitivity of these traps. As they are very sensitive, in fact, they are filled very quickly. So it is difficult to obtain very old age with this method because the traps are quickly saturated. It depends of how we use this method, but it's difficult to obtain age older than 3-4 kiloyears. But we have another method based quite on the same process. It is ESR, electron spin resonance. It is the same story. We have also electrons trapped into the crystal. Here it is quartz crystal. There's two different paramagnetic traps identified, aluminum and titanium, and they are not exactly the same in terms of sensitivity, light sensitivity. You see here, for example, here you see for OSL it's very, very quick, second 2 minutes to be resetted. For the ESR traps, we need many hours to be resetted or many months to be resetted for aluminum. It explains why it's less precise, because sometimes the zeroing, the bleaching, the resetting is not totally complete, essentially for aluminum traps. But the big advantage of this method in regards for OSL, it is the curve you have here after the deposit. You see it's more long, it's longer to obtain the saturation. So it allows to give age for very, very, very long period. For example, using aluminum center, it's possible to give age of sediment deposition between 6 million to 100 kiloyears. So you see it's totally different. And it is possible using OSL or titanium or aluminum in ASR to give a complete evolution of a stratigraphy and a very complex sediment deposit. This method allows, you see here, to date different alluvial terraces, for example, covering all the quaternary period. It is with this method, ESR, essentially, based on aluminum and titanium traps, then it is we give the age of the evolution of many different river into Europe, but not only in Africa, Asia, etc., etc. And the last method I will talk about, it is also ESR, but now ESR applied on teeth, and it is a little bit more different because in this we have to take into account a part of the teeth containing radio elements. So it is complicated to know very well how many electrons have been trapped year after year, because this quantity evolutes into time in regards of the incorporation of uranium during the fossilization phase and the transformation between uranium and thorium. And it explains why the annual dose, is the dose of radioactivity received by the sample year by year, change by time. So it's why we don't talk about just ESR method here, but ESR U-series method, because we have to apply U-series analysis in order to understand how the uranium, thorium moved into the teeth in order to determine well the annual dose and determine well the age of the fossilization of the teeth. The teeth are analyzed by ESR, but we need uranium series in order to understand one of the parameters of this method. It is the annual dose. Another thing for this method you have to take in account, to keep in mind, it is that it is not possible to use on each kind of teeth of all the mammals, because you see we have here the example of a proboscidean teeth, and you have here the repartition of the distribution of uranium into the enamel of this teeth, and you see it's very, very different area by area. It's very complicated to understand and to analyze, and to analyze precisely and to know precisely the amount of uranium in each part of the teeth. And it explains why you have here in 3 different colors the teeth we can use for dating by uranium, ESR uranium series. The best are bovids, equids, cervids, and rhino. No problem. The enamel is very thick. There's a lot of things. It is very homogeneous. It works very well. It's not so good for Ursus and humans because the enamel is not so good, but it's possible. If you don't have other kind of teeth, it is possible to use, but it's not very good. And it is impossible in Proboscidon, Elephas, Mammutus, something like that, not possible. And carnivorous, it's not possible to use this method. So if you want to give age using this method on your archaeological level, you have to focus on bovids, equids, cervids, and rhino. Ah bah tiens, ça revient. This method, you know very well. It's very useful and very used into many different sites because the main importance of this method is that you date directly archaeological fact, the death of an animal, and if you can prove that animal have been eaten or hunted by human, you have a direct dating of an archaeological level.